a great tool we have dealing with any incompressible flow is the stream function formulation. So we are going to define the stream function here as integral from the wall 0, y equal to 0, to any position y. So phi y equal to that, u at y prime times dy prime. All right. So basically, phi of y, you can think of it as how much flow per unit time has gone through the area lies between the boundary and that particular y. So let me draw it over here. So this is the y direction, right? So the stream function phi at this y is basically, there is a boundary layer profile, the flow rate, the integral of this area. So the flow rate across the region between the wall and that particular y. So that's what phi is. And with that phi, and also with the mass conservation equation, we can basically, through the definition of phi, we know u is equal to partial phi partial y, right? And at that, with the incompressible condition, we know that the v velocity is going to be minus partial phi partial x, right? So that is the v that are going to guarantee the satisfaction of the incompressible equation. Okay, so now we have the only thing to do is to substitute the u and v into the momentum equation. So what we get is a equation where my u becomes partial phi partial y. My du dx becomes partial square phi partial x partial y. Okay, so my v is going to become minus, so I'm going to say minus here. My v is going to be minus partial phi partial x, and my second derivative, my du dy becomes the second order derivative phi in the y direction. So this is just substituting the definition of phi into the x directional momentum equation. So the pressure term stays the same, and the viscous term, we still have a nu here, becomes the third derivative of phi in the y direction, right? Because originally it's a second order derivative. Now the velocity itself is a derivative in the y direction, so that's a third order derivative. Okay, so that is the general form of the two-dimensional thin layer equation in stream function form. So the first thing we'll try to do today is to look at self-similar solutions.